So at a given instant, the wheel is rotating with the angular velocity and angular acceleration shown. Determine the acceleration of block B at this instant. So in this problem, we have several bodies, rigid bodies connected to each other. We have the wheel and rod AB. And motion of the wheel will be connected to motion of AB. And our purpose is to calculate the acceleration of block. So here, how should we think? Which formula we should use? We should say B is a fixed point on AB. Okay, so I can correlate velocity of B to velocity of A using the equations of translating axis. So I can just say that velocity of B as a vector is equal to velocity of A plus omega of the rod AB vectorial AB. This is the first correlation I can write, and it will allow me to find two unknowns. The two unknowns are, what are the two unknowns? If I write this relation here, for B, I just know that it's translating in the slot. So I can say that VB and AB should be along this line. Okay. Now I can do some analysis to know if B is going up or down. Because look, if the disk is rotating like this, clockwise, so A is going downward. Okay. So this is why if I do a small analysis, I will know that B will go down. Okay. So if I didn't pay attention, it's not a problem, because when I solve, I will get a negative result. But sometimes I can expect what will be my result. Okay, so I can assume that VB and AB are downward. For velocity, I can always predict. Sometimes for acceleration, it can be decelerating, so it can be upward. Okay, so it depends on the case. Now, what we will do, we will write the vectorial relation, and from the sign of our solution, we will know if our assumption is true or not. But for VB, we will be sure that it's going down. Now, for VB, we just know that it is vertical, but we don't know the magnitude. So we put minus VBJ equals to. Now, concerning VA, A is a common point between the rod and the disk. So I can get the velocity of A by doing the analysis of disk motion. The disk is rotating about a fixed axis. So the fixed axis is passing by this point. Therefore, I can be sure that the velocity of A will be perpendicular to the radius. And from the right-hand rule, it's a downward velocity. So I can draw the vector here. This vector is perpendicular to the radius line. And since I have that this angle is theta, so I can say that velocity is perpendicular to the radius. And if I take the vertical line, it's perpendicular to the horizontal. So then I can say that the velocity is doing with the vertical the same angle between the horizontal and the radius, which is theta. So this angle here is theta. Then if I decompose velocity into ij, it has a negative j component and a negative I component. So I have minus the magnitude of VA. So velocity of A as magnitude is very simple because it's rotation about fixed axis. So it's omega of the disk times the radius r. So then I have omega here and I have r. All I have to do is to replace. So I have 2 times 0.3 equals to 0.6. So now I replace into the vectorial relation. So it's minus 0.6 sine 60 along I And also it's a negative projection along J, so it's minus 0.6 cosine 60 along J plus, now, concerning omega AB, okay, omega AB is perpendicular to the plane. It's along K, but it can be clockwise or counterclockwise, okay? I can do here from my figure, if I do the analysis, I can say if VB is going down and A is going like this, so I can say that omega is clockwise, okay? So I will put omega clockwise. So if I put it clockwise, then I can say that it's minus omega ABK vectorial AB. Now, for vector AB, I will decompose it into two components. So this is vector AB, as you can see here. This is vector AB, okay? Vector AB is doing with the horizontal an angle phi. So I can project it on I by doing plus AB cosine phi along I and plus AB sine phi along J. The length of AB is given. It's 0.5. And the angle phi with the horizontal is also given, 45 degrees. So I do vectorial 0.5 times cosine 45i plus sine 45j. And now I have my vectorial relation. All I have to do is to expand as we do usually and to compare along I and j. The comparison along I and j will give me my two unknowns. What are the only two unknowns in this equation? I have VB, the magnitude of VB is the first unknown. When I compare along j, I can get an equation for it. And by comparing along I will obtain an equation for omega AB. Then I can solve for my system. Okay? Any question on this? Now, concerning the acceleration, I will follow exactly the same procedure. I will relate acceleration of B to acceleration of A. Just I should pay attention to, for point A, to consider the normal and tangential components. So, since A is doing rotation about a fixed axis, then it can be decomposed. The acceleration of this point can be decomposed into A tangential, which is equal to alpha times r. And from the right hand rule, since alpha and omega are same sense, so AT will be downward also to have alpha clockwise. And alpha is given, it's 6 times r, so it's 1.8. Now concerning the normal acceleration is directed towards the center of rotation, and it's given by A normal at A equals to omega square times r, where omega is 2, so it's 4 times r equals to 1.2. So now all I have to do is to relate acceleration of A to acceleration of B by using the vectorial relation for translating axes. So AB is equal to AA plus, concerning alpha of AB, also you can do an assumption. If you assume it's clockwise, okay, so it will be plus, when we replace alpha AB vector, we will put minus alpha AB along K. So plus alpha AB vectorial AB minus omega square AB. Concerning omega, you got it from the previous step. Omega of AB was calculated based on the previous vectorial relation. So just you can now just replace it by its value. And here, remember that this is a number. So here it's a simple multiplication. Okay. And concerning AA, I will just replace it by the tangential plus normal component. For the tangential component, it's like the velocity. It's doing with the vertical an angle of theta. Okay. So, and it has a negative component along I, negative component along J. So for AA, it's the tangential component is 1.8. So it's minus 1.8 times cosine 60 along I, cosine 60 along J and sine 60 along I. Okay. Now, this is the tangential component. For the normal component, also we should project it. So as you can see here, the normal component is along the radius, so it's doing with I in angle theta, and it has a negative component along I, positive component along J, so it is equal to a plus 1.2 times along I, it's a positive it's a negative component, so minus cosine 60I and plus sine 60J. And now, if I replace all terms in the vectorial relation, so alpha AB, if I consider it positive clockwise, I replace it by minus alpha ABK. And all other parameters are known. AB was already determined in the previous step, and omega AB was calculated from velocity relation. So now, the only two unknowns in this relation are for AB, if I replace it by minus ABJ, I will have AB unknown and alpha AB unknown. So I will solve for, here they just ask for AB, so I can just, but to find AB, I will need alpha AB. Okay? Any question on this problem? Just concerning omega AB, I can calculate it using also the instantaneous center method, but here it's more the geometry is a little bit complex, okay? But also it can be done because look, B the velocity of B is along this direction, so the instantaneous center should be along this line, and the velocity of A is perpendicular to the radius. So the instantaneous center should be on the perpendicular, which is the radius, and should be along the radius line. So I can say here that the IC is somewhere here. Okay? And from geometry of the figure, I have this angle equal to theta. And this angle is given to be equal to phi. So if I want to find the omega using the IC method, I should calculate the distances. I should calculate this distance. Okay? To do this, I can apply the sine law. So from sine law, I can write that this distance from A to the IC, so distance from A to the IC over sine phi is equal to AB, which is L, over sine theta. So now from this relation, the only unknown is the distance between A and IC, because pi, theta, and L are given. So once I calculate this distance, I can say that omega AB is equal to the velocity of A, the magnitude of velocity of A is omega times R, which are both given, over the distance that I calculated from the sine law. And in this way, I can find the magnitude of omega AB using the method of instantaneous center. Now, concerning the sense, I will use the right-hand rule. So as you can see here, to be able to rotate, to be able to have velocities downward, using the right-hand rule, I can say that omega of AB should be clockwise. Okay, so this is another method to calculate omega AB. And concerning the acceleration, we don't use IC method for acceleration. We just use it to find angular velocities and velocities. So now once we find omega from this method, in order to calculate the acceleration of B, we will go back to the vectorial relation. Now just here, once I find omega AB, if I want to find VB, all I have to do is to say that V of B is equal to omega AB times the distance between B and IC. So times this distance. And this distance can be calculated based also on the sine law. Okay, so times distance between B and IC. And I can find this from sine law because I can write here that this is equal to distance between B and IC over sine of this angle. And this angle is pi minus theta minus 5. So here we have 60 plus 45, 105. Then this angle will be 75 degrees. So we can say that it's over sine 75. Okay. Any question on the instantaneous center method? Okay. Another problem. At a given instant, gears A and B have the angular motion shown. Determine the angular acceleration of gear C and the acceleration of its center D at this instant. Note that the inner hub of gear C is in mesh with gear A and its outer rim is in mesh with gear B. Okay. So whenever we have gears into contact, the method to use is to try to find what are the common point between gears and do the analysis based on this. Okay, so what do we know in this problem? We know the value of omega A and the value of alpha A, the angular velocity and angular acceleration of this case. So we can find then the velocity and acceleration of any point on this gear. So in particular, one point of interest for this gear is the point of contact between gear A and D. So this point of contact between the two gears will be characterized by a common velocity and linear velocity and a common tangential acceleration. Okay, pay attention, not common acceleration, just common tangential acceleration. So here, if I look at my figure, omega and alpha are clockwise. So from the right-hand rule, I can say that velocity of A is equal to omega A times RA. So VA is omega A times RA. And tangential acceleration of A and A tangential of A is equal to alpha A